Welcome to the ET335 presentation on gate interfacing and control gates. Here I'm showing our gate family interfacing, a little diagram showing how families of TTL devices. So here we have a standard TTL and a standard TTL. So the valid high output by spec goes between 2.4 to 5 volts. The input voltage is guaranteed from 2 to 5 volts, which gives us a noise margin of 0.4 volts. Okay, and the guaranteed output of a gate is between 0 and 0.4 volts. The guaranteed input voltage that it'll allow as a low is from 0 to 0.8, giving it a noise margin of 0.4. So these devices together will communicate nicely. Here I'm showing an HCT Cmos to HCT Cmos. HCTs are directly compatible with our standard TTL. So they're a Cmos device, but they're set up to communicate properly with a standard TTL. So this is our direct replacement. So the devices on Cmos are very tight. So we have from 0 to 0.33, and it'll accept the standard input logic range of a TTL device. So we have a very large noise margin. And we have a very tight output, 4.5 to 5 volts. And they will interface with a standard TTL from 2 to 5. So this device is very tight on the high and the low and will communicate directly with standard TTL. Here we're showing the HC Cmos to the same family. And again, we have very tight outputs and they have a fairly large noise margin. Here I'm showing a cross section of the comparison between the CD4000, which is the grandfather of the CMOS, okay, and we're seeing it connected to a TTL device. So when we go from CMOS output to TTL input, it's okay. It's predictable and it works. However, if we go in the opposite direction, TTL to CMOS, it will not work because our noise margins are out of sync. So this one has a very large output, but our CMOS will not accept it. So there's a lot of cases that these will not work. So we never connect TTL to standard CMOS. If we do need to connect TTL to CMOS, there's a couple ways we could do that. One of them is by using a pull-up resistor to give it the range that it needs to be interfaced properly. Here's another way that we could interface CMOS to TTL, and that would be with a CD4050. It's a device specially designed to connect these two. Here's the gate driving and fan out. What we have here is syncing mode, and we can drive a certain amount of gates depending on the type of gate it is. So here we have an output. It'll drive 16 milliamps, okay? But the gates on the other side will pull 1.6 milliamps when they're in the high mode, okay? So if we do some math here, we get 10 gates. So a standard gate will drive 10 gates in that condition. Okay, so we fan out is the number of gates will drive, so our fan out is 10. For sourcing condition, it will drive 400 microamps, significantly smaller than the 16 milliamps low. Okay, so the gates, when they're low, will take up 40 microamps. So if we do the math, also the fan out's 10. So TTL gates will divide or drive 10 gates of the same family. Here I'm showing enable and disable functions. So we could utilize gates as switches so that we could have an input signal oscillator and we could put an enable signal in and it'll pass that straight on through. Okay, so an AND works really well. So we have a signal in, we put 5 volts in, we get the same signal out. If I disable it by putting a ground on our gate, we have nothing out. It's disabled. We're going to utilize this device for our auto alarm in the future. Here we're using an OR enable or disable. So when we put the clock oscillator in, we put a ground in, we're going to get the output out. And if we put the high on, we're going to disable it, but we're going to disable it with a high output. So we could pass the same signal when it's a low, and we could disable it as a high. Here we have a combinational gate waveform where we have an OR gate feeding into an and we need to evaluate these two separately. So the first thing we're going to do is evaluate the OR gate. So the unique condition is 0, 0 equals 0, so we need to go through and highlight where there's zeros. And hopefully I got them. So now let's change our pin. Let's go ahead and evaluate. So wherever we have two lows, we're going to have a low. Okay, so let's put our highs in. And hopefully we got them. So let me go ahead and let's go back to the highlighter. And let's see where we have our AND gate would need to be high, high. So we're going to need to do the high, high. So why aren't you working? There we go. And we look like we have here. Let's see, do we have anything else? We have, looks like a little sliver here, so we need to make sure that gets covered. A little short. Okay. Let's go ahead and grab the pen and go back and double check we got everything, but let's. Alrighty, so 1, 1 equals 1, so get out of there. Okay. And it looks like, oops, and we got a little sliver there, it looks like. Okay, let's make sure I didn't miss anything here. Okay, I'm going to call that good. Okay, here's our answer. Much, much prettier, but it looks like we did okay.